Hello everyone. So in this video, we are going to discuss the solution of this question, and this question appeared in P Chaitanya GTM 11 this year. The question demands a very sound manipulation over two summation inside the integration sign. You can notice that this first summation 1 is the summation of powers of all sine function, which is starting from 0. And the second summation is the same sine function over the same powers, like starting from 0 to n, but odd numbers are appended in the front. Even if you expand this thing, all these two summations, you get that everywhere sin x is appearing. So we can substitute the sin x as t and its derivative is cos 60x over here. So easily we can understand that the limit 0 to pi by 2 can be converted into 0 to 1, and still we have the two summations, one for the GP of sine and one is the AGP. So how do we do it wisely to get the answer quickly? Before jumping to the solution, I suggest you to give an attempt to this question, because I believe this is the question you must try. So let's see how we can solve it. So you notice that we already observed that the Fn I can write 0 to pi by 2 and y pi by 2. I can just directly substitute the value. T is equal to sine x. So our dt will become cosine x dx. And the limit value will turn into 0 to 1. It's not the difficult thing to understand. Now this will turn into summation. A goes from 1 to n, t to the power k minus 1. This is the first sum, and the second sum will be summation k goes from 1 to n to k minus 1, and that is going to be t to the power k minus 1 again, and this is dt. So this much everyone can understand, everyone can think. From there, how do we manipulate these two summations wisely to get the answer quickly? Let's see. This summation I'm assuming as, let's say, p, and this summation I'm assuming as q. And I want to write the general term of the product of the two summations actually. What I mean to say that the p I can write in the expanded form as 1 plus t squared plus t cubed, and all the way up to t to the power n minus 1. Similarly, the q I can write here is the first term will become 1 into t to the power 1 into t to the power 0, that is 1 again, so 1. Then the second term will become 3, so 3 into t to the power 1, then 5t squared, then 7t cubed, so on, and at the end 2n minus 1 and t to the power n minus 1. Now my point is, can we write the product PQ in one single expression? Means I simply give the indexes and I get the term what we actually get after multiplying P and Q. So try to notice. What I can notice is, if you want to write P into Q, I can write in this way. Let's see. I'm trying to give the index for the first summation. There's a 1 1 1 everywhere, the coefficient is 1. So what I'm going to do, give it that The summation I starts from 0 and it goes up to n minus 1, and I'm giving t to the power I. Do you see that if I start putting the values of I starting from 0 and goes up to n minus 1, they will produce t. And similarly, I'm going to give that other index to the q. So for the q, I want to write something else. So for that, I'm going to give us the summation again here, and that is for j actually. So j starting from again 0 and goes up to n minus 1. Now how do we write this j here for the t? It is actually 2j plus 1, because when I substitute j is equal to 0, I will get this one there. So basically it's a red one for this j part and the blue one for the I part. So this is for P and this one for Q. So 2j plus 1, and then I can write t to the power again j. Now notice one thing. Suppose I want to find this product of 1 and 1. It means I have to substitute j0 and I0. If you substitute I0, that will become t to the power 0. And if you put j0, that will give him 1, and t to the power 0, that's 1. So we get the product 1 into 1. That is 1. Similarly, suppose you want to find the 1 into dt. That means I need I0 and j2, because the second term I'm finding for the j index. So j is equal to 1 actually, by the way, because starting from 0. So j is equal to 1, sorry, 0. No, I is equal to 0 and j is equal to 1. So I is equal to 0 will give you 1 there, and at j is equal to 1, it will give you this thing. And of course, when you multiply this 1 into this, the power of t should be 1 only. But similarly, you can check for this t square, and let's say 5t square. So t square is coming with j is equal to 2, and sorry, I is equal to 2, and 5t square is coming from j is equal to 2. So we substitute j is equal to 2 and I is equal to 2, you get this product. I hope you understand this thing. So now I can write in more clear way. That is, I'm writing first I0 to n minus 1, and again I'm writing j here starting from 0 to n minus 1, and you can notice that I can add the powers of t there. So that will become 2j plus 1, and that is t to the power I plus j. So that is a placeholder of this p into q in one single argument of the two summations. So again, I'm writing this fn here in terms of the new derived way, 0 to 1, and in the place of the pq, I'm writing this whole product, what we just discovered. So let's substitute it here. This is going to be summation. I goes from 0 to n minus 1, and summation j goes from 0 to n minus 1, and that is going to be 2j plus 1 into e to the power I plus j, and there is dt because we are integrating. Now notice one thing, in this entire integrand, the only variable is t over here. All the terms are actually constant term because they are constrained or conditioned to this summation, and the index is I and j. So this t we can integrate alone. It means we are switching or swapping the summation over integration. It means this tells that we have to do the summation first, but we can swap the process. And that process, what we can do is, I am just taking the summation out like this, all the two summations I took it out, and 2j plus 1, and I'm giving the integration first. It is actually a very common thing we can do whenever summation and integrations are together. And notice the integration of this t to the power I plus j, the integral we can find easily, I0 to n minus 1 and j0 to n minus 1, and that is going to be t to the power I plus j plus 1 by I plus j plus 1. So that will giving you 1 by I plus j plus 1 after all the calculations of the limit. And oh, there was a 2j plus 1 I forgot to write. Let me adjust it. That was 2j plus 1 over here. That is I goes from 0 to n minus 1. Then summation j goes from 0 to n minus 1. And that is 2j plus 1. So after this, you can now notice that this the integrand or the integral also give the values in terms of ij and so on. It means now this whole thing together, we can find it out over these two summations. But there's a trick. What the trick is, let's understand. You notice I can write I goes from 0 to n minus 1 and summation j goes from 0 to n minus 1, and this is 2j plus 1 divided by I plus j plus 1, and this is our Fn. Now the integration is out of the scene. We are now playing with the double summation, and many students knows how to deal with this kind of situation whenever we have the double summations. So see here what is happening. This in denominator we have I plus j plus 1. So if you swap the j and I, it will not affect. It means it will not give you any trouble. So what I'm going to do is I am taking, because the index for the I means I index is also running from 0 to n minus 1 and j is also running from 0 to n minus 1. So if I just switch the j and I, this will give the same value. It means that I can write the Fn again by just writing I goes from 0 to n minus 1. Summation j goes from 0 to n minus 1. And I'm this time writing j as I. So I can write 2i plus 1 divided by, and also I plus j plus 1, because in denominator if you switch, it will give the same result. But notice that numerator has some significance changes. But at the result, there will be no change. But this will make our life easy to calculate this summation quickly. How we can sum? Let's say this is 1 here and this is second here. I can add them together. So we get twice of Fn. And since they are the summation of the same index running from same starting to same end, so I can write here summation I goes from 0 to n minus 1, summation j goes from 0 to n minus 1, and then you are adding the numerator because denominator is same. So we'll get it twice of I plus j plus 1, because this will give it 2j plus 1, 2i plus 1. So we'll give it twice of I plus j and plus 2. So we can take 2 common. So they'll give you I plus j plus 1 in denominator, and notice what will happen. This will give you the I plus j plus 1 cancelled. And so we get Fn is equal to nothing but I goes from 0 to n minus 1 and summation j goes from 0 to n minus 1, and here only 1 we left out. Now what we do? We first do the inner summation. So you are adding 1 n times because starting from 0. So that will result n. So this will give you the summation I goes from 0 to n minus 1 times n, of n. And now I can see that the n you are adding again n times, so that will give you n square. So you got Fn as n square, and anything you want you can find it. So I have to find F21 minus F20, so nothing but it's 21 square, 21 square minus 20 square, and this will give you 21 plus 20 into 21 minus, and that results to 41. That should be the answer. In this way we found this question easily. Not so, but still we can understand how it was very intuitive to do like that. The trick is that here is this one, I plus j plus 1 and this 2i plus 1 here. If they're symmetric enough to get cancelled after getting this summation, this is a kind of integration you have done many times, 0 to pi by 2 sine square x kind of integration, what we call a King's rule or the Queen's rule. So the similar way we are operating on this two summations. But the trap can be difficult when we have no such symmetry. And of course, they will not ask those kind of questions in the J domain because that is not in the scope of that. I mean to say that if suppose they ask you this kind of trap, like a 0 to 1, let us say, and they give you 1 plus, let's say 2k plus 1, or let's say 2k minus 1, what I'm writing. I meant to say this one. Let's say here summation k starting from 1 to n minus 1, and that is 2k minus 1 into t to the power k minus 1. This is the first summation. And if they give you like k is equal to 1 to n minus 1, and that is, let's say, something 2k plus 1, or maybe 3k plus 1, let's say, a little bit more complicated, 3k and tk minus 1. And then they ask you to find this summation or the integration. It'll be difficult because we cannot generate such a nice kind of this argument of the double summation so that it can be easily cancelled, because this was so symmetric that denominator was not changing. But in this situation, maybe there is some difficulty. So of course, this kind of question they will not ask because not in the scope of the J and all. But you can expect these kind of questions, and you have done this summation, double summation type of questions in the binomial theorem, so you can do it. So for you, I can give you one question. You can try this. Let's say 0 to pi by 2, similar kind of questions I'm giving you, 0 to pi by 2, and this time I'm giving summation. Let's say k goes from 1 to n minus 1 to n 2k plus 1 sine to the power k minus 1, and the second summation is k goes from 1 n minus 1, and here I'm giving you not 2k, 2 times sine to the power k minus 1 x, and this whole dx. I don't know what answer will come, but it's a good practice if you want to practice through this. So that's all for today. See you in the next video with some other such questions. Stay math active.